Hello, everyone. Uh, so this week we'll be talking about semi-Markov systems. Um, it's kind of a continuation from the previous week. And as usual, I am waiting for 10 minutes since my student has joined. So I'll just continue with whatever I have to cover. And this session will be recorded and made available on YouTube. So students can view it at a later time. So, with that, let's get on with today's session. So today's topic is semi-Markov systems, and this is the second last session that I'm taking. Next week will be the last session, and hopefully this this is good to the students. And I believe the final exam of this course is on April 30th. So I will hopefully you'll have something to give from these sessions. So starting with today's topic, MV1 queues. So in the previous week's session, we primarily discussed the mean formulas and the polar championship mean formula. And in this lecture, we'll be doing a bit deeper analysis. So there is a lot of study on waiting times in a queue. So that once you are in the queue, how long you have to wait, and so what are the state probabilities of the waiting state, as in what is the number of packets that are in the waiting state, and so on. So so you can kind of use these notes that I've prepared while I was reviewing the lecture myself for your own reference. And I kind of summarize all of the important formulas that you might need. And so there is also a detailed analysis of the busy period of the queue. And so there is a way of obtaining it from the theory of Markov decision processes and from the exact busy period distributions and service time distributions and all that. And you can also obtain it through a different argument, through the regenerative process argument that is already known. And and then there is some other discussion on NG1K queues, where the polar championship mean formulas are not applicable because the system that is not completely like an open Jackson network. There are some issues after capacity of K packets start getting dropped. So then the analysis changes, and then there can be further modifications such as impatience and bulking, and which can further complicate the system. And then we study MGCQs. So both, and then MG infinity queues, if we take C opposite to infinity. And then we can find the probability of the states of the state and for all of these systems. And all of these, and the final one is MBCCQs, for which the Erlang's B formula holds. And all of these come under the ambit of semi-Markov systems because the arrival process is Markovian, the departure process is not. And so then there can be further extensions of batch type service, batch type arrivals. And then we can have GM1 queues, where the also a semi-Markov process because the service process is Markov, the arrival process is, and we can have any general distribution. And then the GMC queues that are embedded Markov. So let's start. That have the GMC queues has an embedded Markov chain. So that's how they're semi-Markov. Start today's problems. And so the initial set of problems actually will essentially use some of the results that we learned in the previous week. So this is from week 10, where we studied renewal processes in some semi and initial theory of semi-Markov processes, and most importantly, the Polish and clinching mean formulas that we studied. So we will do some problems based on these, and then move ahead and cover some problems that are based on the latter topics. So we wait for the screen to stabilize, and okay. So first, like conceptual type question. Okay, so let's say we have the state of the system at departure is like, so this is denoted as BM, state of system at departure. And then we have PM equal to state of system in Q. So while in Q, so it's not in arrival, not in departure, but in the Q. So the question is, like, let's denote it in something like Q1. And so the question is, so and this is kind of short notice, short thing, because Bn is essentially the probability that the system is at state n at departure, and this is the probability that the system is at state in Q, right? Well, in Q. Or just as an external observer. As external observer. Right? So can equal to Q1. That is the question. So R in the state probability is equal for departure, and in general, the answer is yes. Also, it's not yes in general. The answer is depends. So it depends on what kind of Q it is. We cannot really, this doesn't hold for any GG1 system, but it does hold for MG1. So for an MG1 system, this relation holds. Otherwise, this relation does not hold. So we cannot say for sure that the state of the system in while of departure will have the same mathematical probability distribution as the state of the system as an external observer. But I should change this to as external observer. Hello. Hello, can you hear me?
Yes, sir, I can hear you.
Okay. So As I was mentioning, so today is the second last session. So I'm covering week 11's content, and um, so here we will be discussing semi-Markov systems today, and there is one more session left, which I'll cover next week, and I believe so. Then so that in the next session I'll be discussing DG1 queues, and so those are like completely generalized queuing systems. But this week, I'll restrict to MG1 queue. So this, I believe, is still will probably lecture 36 or something. We'll check. Um, 1 second. So I think the exam for this course is on 30th April. So the final certification exam. So I'm on track, I think. And next week, yes, like uh, next week, if students are there and if time permits, I'll like you can do a doubt clearing for whatever time that I have. I can do a doubt clearing for all topics, so that can be done. Yeah. So today's this covers lectures roughly uh, 40 to 43, I think. 40 to 43. But there are some things from previous lectures as well. So I will, as usual, uh, while I prepare for the session, I usually watch the NPTEL lectures myself and I prepare notes. So these notes can be useful for you as well because you might have to refer to the formula. And so I had started discussing uh, this particular question. I can repeat it. So, so here's the question that you have a general queuing system, and so Bn denotes the probability that there are n elements in the queue when you are observing a departure tone. So you are yourself uh, you are a packet or a customer in a queue and you are departing the queue. You are just leaving the queue, and at that point you are observing the system and you are seeing that there are n people in the queue, n customers in the queue, n packets in the queue, whatever. That is so that probability is Bn. And then the probability that as an external observer, you are watching the queuing behavior and you see, and at any general time, you are seeing the number of elements in the queue. And if that number is n, the probability that the number is n is qn. So is Bn equal to qn? That is the question. And the answer for this is kind of it depends. We cannot write this in general for any queue, but for MG1 queues, that is when the arrival process is exponential and the departure process is a general process with a single server, it holds. So the state of the system that you observe as an external observer is the same as this, has the same probability as the probability distribution as the state of the system which you are observing as a dip while departing the queue. Okay. That has left, so I'll just wait for a bit. Hello. Okay.
Hello, sir. There's a
Uh,
network issue.
yeah. Okay. Yeah. Yeah. That's okay. Can you hear me now?
Yeah.
Okay. Okay. So did you get this question? I just discussed it a bit.
Yes, sir.
Okay. Okay. So then let's do some more problems. And
Can I interfere, sir? How will be the
yeah,
questions like for the examination?
for your
Is
exam,
the
for
is
your
the
exam, so
entirely 50 questions are descriptive?
I have no idea about it, unfortunately, because I am really not involved in setting exam papers or anything of that sort. That will be only decided by the course instructor. Um, I, I am actually I'm actually not in any communication with the course instructor whatsoever because this is kind of independently I have to do. I just with my own knowledge, whatever I know, I'm trying to help students what I can. Regarding the exam, I'm not involved in any activity regarding the exam. I'm not preparing assignments or setting question papers, nothing like that. So it will all be done by the course instructor himself. And the best I can suggest you is that you should really do the assignments properly because the assignments themselves have a good variety of questions of all kinds that help you understand the topic better. And if you have time on top of that, you can go through the problem sets of the book that I've shared in the drive link, which is Berserkers and Gallagher. So I've uploaded, it's freely available online. I've uploaded it in the drive link as well. So you have for chapter 3 for queuing, so you have the questions as well as the solution manual. It's all uploaded. So that can be a really good handy book for some extra practice if you want. But first and foremost, I think it will help you to go through the assignments themselves because like the assignments are in itself they cover a lot of ground, lot of topics.
Okay, thank you.
Anything else?
No, sir, thank you.
Okay. Okay. So let's continue. And so then let's do a short exercise. Okay. Let's say the service, so the service time, which is for a queuing system, service time distribution, service time CDF is given as B of X. And now the question is, so what is so first is CDF of, like there can be two parts here. First part is, what is the CDF of residual service time? Service time, let's say C of X. And the second question is PDF or the probability distribution function of residual service time, something like small c. We want to find out both. Now, if it's always helpful to find CDF first, right? So, by residual service time, what we mean is at any point in time, you want to find out how much service time is remaining, right? So some service is ongoing for a customer, and sometime in between the service, you stop and then you ask, okay, how much time do I have left in order to be able to complete the service, right? So that is kind of the question. So, okay. Right. So the first part is the residual service time is the C of X is essentially the probability that residual service time is less or equal to X, right? So then the residual service time is less or equal to X. So let's say there is some total service time S minus some kind of service time that has been completed. S is less or equal to X. So completed service time, so something like B of S. Let's denote it as B is less or equal to X. So over here, one thing to notice, B of X implies that the probability that the service time, which is total service time, which is probability that the total service time is less or equal to X, right? So that is B. And then actually, the thing which I'm trying to derive is I'm trying to derive C of X in terms of B of X. How do I obtain this, right? It's probability that actually so V of X is essentially probability that the busy period, the service period, is less or equal to X. Let me change this to Y. And so here what you essentially end up having is probability that B is greater or equal to S minus X, right? So if you just change the size, and so that is nothing but 1 minus probability B less or equal to S minus X, right? And so that is 1 minus B of S minus X, something like that. Now, before like really doing that, S is itself, the total service time is itself an unknown quantity, right? It's unknown. And so we need to take an expectation over S, right? Because it's unknown. So we need to take an expectation over S. So that's what we'll do today. Hope I'm doing it correctly. So you can take this to be 1 minus expectation of identity function of let's slightly take a different one. So this is probability S is less or equal to B plus X, right? So I think this follows from one of the famous inequalities that I can just take this as expectation of S from, this is from probability theory, that I believe this is this can be derived from Jensen's inequality. That this is, yeah, this is like expectation of S comes into the denominator, and then what we have is some kind of then probability to check on this. B plus X minus, it should be probability S by making some error here. But well, actually, I'll check the derivation once again and update my notes. But the answer for this CDF comes out to be actually X minus integration of B of X dx, B of S ds, something like from 0 to X by expectation of S. So this is what the CDF comes out to be, right? So it's dependent on the busy period CDF, and then the PDF actually comes out to be 1 minus, if you take this the derivative of this, I'll work out the derivation by myself and try to update the notes. The PDF comes out to be this quantity. So this is an important property to keep in mind, that for the residual service time. So if you know this is the CDF of service time, and this is the CDF of residual service time, and then this is the expected service time, so this comes into the denominator. So this is expected service time. So I'll update the derivation later. But so this is an important kind of formula to keep in mind, and you can solve a small problem regarding this. So let's say, using this concept, which is, let's say, problem 3, we have MD1 system, and expected value of service time is known to be 1 minute, right? So how do we characterize? So then residual service time, like the question is characterize residual service time. Okay. So the service time is 1 minute. So what will the service time CDF look like? So B of X. So if you have to draw the PDF B of X, so this is clearly at 1 minute. We have something like Dirac delta function, and then otherwise it is 0, right? So that's the PDF, because the only value at which there is some, it's a deterministic function. So the only value of service time that holds is actually the mean. It is 1 minute. It is deterministic. So it is something like delta of x minus 1. So if you integrate it, the CDF will be something like, it will obviously, if you integrate it, it will be 0 for all x less than 1. And it will be 1 for all x greater than or equal to 1, right? This where x is in minutes, of course. X is in units of minutes. So then from this, you can compute the residual service time PDF using this formula. So you have 1 minus b of x by expectation of s. So then this just becomes very simply expectation of s is 1, and this just becomes 1 for okay. Unfortunately, I think I have to proceed without because of some issues at the end. So let me do that. Unfortunately, um, I hope this YouTube recording will help us. So if you take 1 minus of this and like accordingly, so then of course still x cannot be 0, so it is essentially 0 or 0. So it is 1 for 0 less than x, sorry, less than 1. And it is 0 otherwise. Right? So this kind of problems can be solved. And so we can solve some more problems based on the mean formula itself. So remember from the mean formula for MG1Qs, the waiting time is given by lambda expectation of s square by 2 1 minus rho. And so, and we also know that the distribution of the mean formula for the expected value of residual service time is expected value of s square by 2 expected value of s, right? So the question is, what is the value of WQ in terms of the residual service time? And so we can quickly find that out. So WQ by R equal to expectation over S square gets cancelled. And so what we have is essentially, and 2 gets cancelled. So we have lambda times expectation of S divided by 1 minus rho, which is nothing but rho by 1 minus rho, because rho is equal to lambda times expectation of the service time as per notation. So then that is handy relation to have. Yeah. And so let's solve now a practical problem using this formula. This 5, this problem number 5. So let's say we have a system where we have a queuing system MG1. So this 4 question is for the MG1 queuing system, of course. We have an MG1 queuing system again, and so there is a queue, and So let's say there is some service time new, and then it leaves, right? Now there is a slight twist. So when a job enters a service, so let's say arrival rate is lambda. So a job enters the service, there is a coin toss upon arrival, right? And and then probability of heads is P, probability of tails is Q, which is 1 minus P. It's Bernoulli trial. And so for tails, no service is performed. And so essentially, service time is something like 0. And for heads, service time follows an exponential distribution with parameter Q, right? Actually, association with parameter mu, let's not use Q, increase, right? So then the question is, what is the mean queuing delay WQ? Now, clearly, it's an MD1 system, so WQ is given by the formula lambda expectation of S squared by 2 times 1 minus 0, right? And where rho is itself is lambda expectation of S. And so we maybe need to find expectation of S and expectation of S squared, right? Now, let's first find expectation of S in this situation. Expectation of S is essentially, so with probability Q, which is 1 minus P, there is no service. And with probability P, the mean service time is 1 by mu, right? This is also like it as Q. With probability Q, there is no service, and with probability P, the mean service time is 1 by mu, right? Because it's exponential with parameter mu. So then this becomes something like something like P by mu. And then you also have to find expected. The value of S squared. So that is something like Q times 0 again plus P times. Now for a exponential random variable, the mean this is the value of the like 2 by mean square. So it's a value of the variance. So it's 2 times p by mu square. And so, and we can also actually write the the distribution of the service time as something like 1 by mu. It is q time. So q is the probability that the that the PDF is exactly zero, or the value is exactly zero, and then p is the probability that the value is an exponentially random variable with this distribution. Right? So x greater than equal to zero. This is the service time distribution. And so if we just plug in these values, then so rho is lambda e to the s. So lambda is the rho by expectation of s. So if we use uh, so if we do some substitutions, then what we have is WQ equal to lambda times expectation is square, which is 2p by mu square divided by 2 times 1 minus rho, right? And so expectation of s is p by mu. So lambda times p by mu times 2 by mu divided by 2 times 1 minus rho. Sum. And then lambda times expectation of s, this whole quantity is actually rho. So what we have, and if we cancel off 2, then what we have is rho by mu times 1 minus rho. Right? Something like that would be the answer. Then solve problems where you have general service distributions. So with that, let's move to the topics of this lecture. So okay, problem number 6 we can discuss, and this is on an MGCC system. So an MGCC system, so what we have is we can immediately write. I'll write the problem later, but we should keep in mind the Erlang's B formula, the most formula, C formula is R to the power C by C factorial divided by summation equal to 0 to C R to the power I by I factorial. So this is the probability, and there is a blockage, and then R is lambda expectation of S, very simple. And so we have, let's say, queuing system. So we have a queuing system where there are, like let's say there is a CPU with there is a there is a data center, data center with which is with 5 servers available, and cost per server, the cost of maintaining a server is, let's say, um, is like something like 100 rupees per day. So this includes everything. So electricity, cooling, etc., etc., etc. And so I did the electricity, cooling, etc. And so there is, and so you have you have students who access the server and access the data center, and they want to use the service, right? So let's say you have like 10 students per day, right? So students use student, let's say, users are at arrive at lambda equal to 10 per day at the server. 10 students that use the server in a day. And main use duration, which is accepted value of s, is equal to let's say something like half a day, right? 0.5 days, right? And the cost of rent, and like let's say the university has some kind of let's say the university has some kind of costing system. So let's say the students PI for the students or the projects that are concerned is charged. It's charged, let's say, for every day that the student is a server, they are charged something rupees. Let's reduce this. Let's say it costs per server something like 80 per month, and then the PI is charged, which is 100 per day for the server. So, and then like it's and then of course there are only 5 servers available, so there is a capacity constraint. If all servers are busy, if all servers are busy, what happens is the request is declined. And so what we want to do is we want to find out mean profit or mean profit of the data center. Right? And so let's first check the block, right? Check the values that we have. So we have for this MVC CPU, we have C equal to 5. We have lambda equal to 10 per day. And we have expected value of service time is equal to 0.5 days. Right? And so the common dish R is nothing but lambda expected value x, which is 10 times 0.5, which is 5. And so uh, so the average number of average hash service customers, students, and let's say the average number of service students is something like R times 1 minus B C comma R using Little's law. So that is the this can be derived. This is something that actually follows from Little's law. The 1 minus BCR is the probability that 1 minus BC from R is a probability that you will not be blocked. And if you are not blocked, the average number of R is the arrival rate times the average service time. So the average number of students per service is nothing but R, provided there is no blocking. So even some common sense. So this is nothing but lambda expectation. So, so then this European was we can obtain B 5 comma 5 as from the calculator. So I will just use online and the calculator. So this actually comes out to be 0.285. And so that, so what we have here is L is equal to 5 times 1 minus 0.285, which is, let's do a quick calculation. This comes out to be 3.575. That's the answer. And so this is average number of service students, so the profit will be L times the service charge, which is 100, minus C times 80. Okay? C is 5. So 100 times 3.575 minus 80 times 5. Let's see the answer. Because 80 is what's per 7. And so this comes out to be actually minus 42.5. So the data center actually operates at a loss in this case. So that's important. It's useful to have this kind of calculation in handy, so that you can find out if the data center or if our facility is actually running properly, right? So even this uses, I'll say, the main formula and some other results. Now, for the 7th and 8th problems, we will deal with G and 1 systems. G and 1 systems. And so, and we'll be doing some problems with respect to that. Yeah, so I'll at this point take a short break and I'll be back in 2 minutes.